Hello, chemistry of Earth and Space Science students. This is the last video of the Toxic Tides unit. It's the second video of Lesson 6, talks about ocean acidification. So this video, or this PowerPoint, comes from a professional organization. So some of the wording is a little out there. So what are we going to do? We're going to try to define what ocean acidification is. We're going to try to explain the chemistry that is involved in ocean acidification. We're going to identify causes. We're going to talk about ecological consequences. And then also finally discuss a few solutions and things that might be done in the future to help. And the main reason for this is that ocean acidification is having a very significant impact on our planet at the moment. We're all aware of climate change and we're all aware of global warming. A piece of that is the amount of carbon dioxide, our carbon footprint. And that carbon dioxide that's in the air is now getting into the oceans, causing it to become acidified, becoming more acidic. So this video, I'm not going to show this, but this video I have linked in your Schoology classroom on demystifying ocean acidification. It's a really, really good video. It's just a little long, and I did not want to include it in my YouTube video for fear that it would get banned or I'd get some type of negative ramification. So you can go ahead and watch that. Again, I've linked it in your Schoology classroom. So this is done by the chemistry, the U.S. Department of Commerce. Why am I having a hard time talking? And it talks about ocean acidification. And there's been some stuff adapted where we've done a little bit of tweaking and adding on our own, but a lot of this information comes directly from the Department of Commerce. So what is this ocean acidification? Well, as the name implies, it's the acidification to becoming more acidic of our oceans. So what happens is it's a chemical process where carbon dioxide in the air gets dissolved into the water, and as a result, the water's pH decreases, and you get a dropping of the pH because of the carbon dioxide. So how does this work? Well, first off, the ocean's water, just because it's water, is going to absorb carbon dioxide from the atmosphere. There's a lot of human activities that release carbon dioxide. The three that are shown here, you got factories, you got gas-powered or petroleum-powered, either be diesel or gasoline-powered vehicles, and then also forest fires. Whenever you have a combustion reaction, something is burning, you're going to have two products. One's going to be water and one's going to be carbon dioxide. So just the burning of wildfires causes a great increase in the amount of carbon dioxide. When too much carbon dioxide gets in the ocean, it starts to harm the organisms. We're going to talk a little bit about how that happens here and how that has an impact on the diversity of animals that are in our oceans and most of our aquatic environments. So how does this work? So the ocean is what's called a carbon sink, meaning it is going to absorb carbon dioxide and it's going to hold on to it. As the stat says here, 30 to 40% of the carbon dioxide released by humans turns out being dissolved into the oceans, rivers, and lakes, all those water bodies. Then there's a couple processes, one physical, one biological, that moves some of the carbon dioxide deep into the ocean where it gets stored. Now that process of grabbing the carbon dioxide and then storing it deep into the oceans is called carbon sequestration. This video here, called the biological pump, is one that kind of shows what that is. I'm going to go ahead and it's 4 minutes long. Again, I'm going to link it in your Schoology classroom to watch it, but it talks about how carbon dioxide gets into the water and ultimately becomes part of the fossil fuels and the remnants of organisms at the bottom of our oceans and lakes. So a really good video, but again, for copyright infringements, I can't show it on my video. So here's basically the carbon cycle in a nutshell. So if we have our factories cranking out carbon dioxide as a whole and just general dust, what's going to happen is that dust is going to follow and is going to go over top the oceans and basically give places for some of these pollutants to be caught, including carbon dioxide. But also, right here, they show iron dust as being blown by the winds, and the carbon dioxide that comes from all of the just us living in an urban area is going to be caught by that dust, and then ultimately it's going to be taken out to sea. And where there is that interface between the air and the sea, there's going to be some exchange of carbon dioxide. Now it works both ways. Some carbon dioxide from the air is going to go into the water, and some of the carbon dioxide is in the water is going to come out. So it's like a cycle. However, when that carbon dioxide gets into the water, you start having a couple effects take place. You got phytoplankton, they take up the carbon dioxide, they need it to grow. Zooplankton, they eat the phytoplankton and they respire or release carbon dioxide. And you turn out having all this carbon that's in the ocean that turns out being the decayed phytoplankton, zooplankton components. That's going to be dropped down to the deep depths of the ocean and forming what turns out to be fossil fuels, or just lots and lots of carbon incorporated into the rocks. Now, they talk about here, there's only a small percentage of the carbon reaches the deep sea. We're not talking about a huge percentage, but some of it does, and some of it gets buried down there for a long, long time. So if it's in the rocks, it can come up because, we have oil wells and such, and when the rocks eventually are lifted upwards towards land, then they get a chance to release the carbon, and it starts all over again. The plants absorb the carbon dioxide and is allowed to decompose, and turns out releasing into the carbon dioxide, and it's just a vicious cycle. This cycle is another way of looking at this carbon sequestration. So how does this work in the oceans? So it's pretty simple. What happens is the carbon dioxide, that's a gas, comes in contact with the water, H2O, which is a liquid. And when they come in contact with one another, they form this H2CO3 molecule, and that's carbonic acid. So the fact that carbon dioxide is dissolved into the water makes the water more acidic, has this carbonic acid there. Now, it's not a really high amount. This process is relatively small doses, but it's enough to make some significant changes over time, since we have so much carbon dioxide, make some significant changes to the pH of our oceans and waterways. So we've already talked about the pH scale. This is like a retread from the last video. But pH is a way to measure the acidity. And the low numbers are more acidic. The high numbers are more basic, or are the opposite of acidic. When you have a high concentration of hydrogen ions, that means you've got a whole bunch of these acidy parts. This with H plus is the part that provides the chemical activity of a acid. Low pHs give you high hydrogen. That's the math. You notice here they have long lines here of the variable amounts of hydrogen. So if you have the amount of 1 at pure water, then you have 10 times that if the pH were 6. That one jump in pH units is a 10-fold change in the amount of hydrogen ions. And it works the other way too. You get 1/10 from 7 to 8. Now you have 1/10 of the hydrogens, 1 to 8 to 9. You have another 10th of that, so a total of 1/100th of the amount that was in pure water. This is a logarithmic scale. It changes very, very dramatically, very aggressively with the concentration of ions. Now we use pH because it's easier to do that than saying this is the concentration of hydrogen ions in a solution, and sometimes those numbers are really, really small. But we can use the scale to measure, or at least see trends in pH. So here is a graphic that shows that between 1751, when they first started collecting data on ocean's pH, and 1994, which is when this particular image was created, they noticed that the pH of the water changed from 8.25 to 8.14. And you might say, that's tiny. That's a really tiny amount. But because this is a logarithmic scale, and going from 8 down to 7 is a tenfold change in the concentration. That small change of 0.11 in the pH actually represents a 30% increase in the amount of hydrogen ions that are in the ocean. Easiest way to put that, you're increasing the amount of acid in the ocean by a factor of 30%. Now, that's a long time, but let's think about what's happened. Most of that time is like the latter part is the industrial generation, industrial revolution, and all the transportation issues we have in the air. We have a change. Look at the graphic on the right. This shows you how much the pH has changed in that time frame. They're looking at 1700s versus 1900s. And you'll notice that where there's the biggest change, remember a negative pH change is an increase in acidity, is up between North America and Europe. No big surprise. Now, what is kind of a surprise is this band down here of dramatic changes. Hard to explain why that happens, but obviously there's a little bit to do with how Antarctica is handling the carbon impact. But yeah, there's a pretty good increase down here of the acidic nature of water. But a lot of it, the biggest changes are right up here between North America and Europe. So how does this have an impact? Well, one of the first things it does is it has a really, really aggressive impact on shell formation. Now, who cares? But this is the shells of crabs, oysters, clams, mussels, scallops, all those things with a shell exoskeleton. Most of them will undergo either a need for increasing the size of the shell, like for oysters and clams, or in the case of crabs and shrimp and lobsters, they require them to slough off their shell and make a new shell. Well, what if we do something that affects the formation of that shell? What if the water becoming more acidic starts to affect the creation of those shells? Well, that would be bad because now crabs, shrimp, lobsters, those shellfish would be hard-pressed to form their shells. So what happens? So it turns out that this happens in like 3 steps. So if you increase the carbon dioxide, as is mentioned up here, the pH goes down. Yay. Okay? So that's like we're just making the pH, the ocean water, more acidic. So we already said when carbon dioxide gets into the water, you make carbonic acid. Now here's the part that's a killer. That carbonic acid will react with calcium carbonate. So what? Well, here's the deal. Calcium carbonate is what the shells are made out of. That calcium carbonate is what the shells are made out of. So the fact that the ocean has become more acidic on the first level is it starts to deteriorate or react with or destroy the shells of these shellfish. It does that by reacting and becomes the calcium ion and the bicarbonate ion. So it dissolves your calcium carbonate. That's called dissolution. So it happens when you have a low pH. If the pH isn't as bad, maybe it's in a neutral range, what's going to happen is you're still going to have the carbon dioxide come in contact with water and make carbonic acid. But here, what's going to happen is the carbonate, the bicarbonate that's made as part of the dissolution, will combine with some hydrogen ions, and then you're going to get a gentle change of making the carbonic acid, which could actually reverse this. So it's not as aggressive in neutral conditions, but in acidic conditions, it's literally tearing apart the calcium carbonate that is part of the shells. Now, what if we're in basic conditions? And we know our ocean is basic. We saw those numbers, right? 8.25 and 8.14. They're basic, slightly basic. What happens in basic conditions? Well, still have the carbon dioxide is going to react with the water to make carbonic acid. That carbonic acid is going to react with is going to break apart into bicarbonate ions and hydrogen. It's going to split those two pieces apart. And then that hydrogen ion that's made is going to combine with carbonate, not bicarbonate, but carbonate. And why is that good? Well, then you have a situation where the carbonate can react with the calcium that was made back here, and you can get your calcium carbonate back, and it could be more calcified. You can have it's called a calcification. So if you're in basic conditions, the more basic it is, you actually have this situation where it breaks down, becomes carbonic acid, becomes carbonate, but you get a creation of calcium carbonate, which is what makes up shells. That's good. However, if we're in acidic conditions, lower pHs, then it doesn't get over here. It doesn't make the calcium carbonate. It only breaks it down and making it much, much harder for the shellfish to make their shells or to even survive because their shells are being reacted with from the acidic water. That's bad. So what are some other impacts besides just tearing up the calcium carbonate? So some things were mentioned in that first video that I said you should watch, the one with the biological impacts. That was pretty good. They talk about how carbon dioxide in the water makes some other subtle changes. Again, when carbon dioxide is dissolved in water, it makes carbonic acid. That carbonic acid breaks down to become bicarbonate and hydrogen. Just showed you that. The hydrogen ions combine with the carbonate. That's awesome, and create the carbonate, decreasing the amount of carbonates available, which means you are going to have less carbonate to be able to react with your calcium to make your calcium carbonate. So therefore, your marine organisms, like this snail on the right-hand side, they need to create the calcium carbonate, but if there's not as much carbonate available, that's going to make it where you're not going to be able to make shells. So the calcium carbonate is a material that's made up of the shells. If you don't have the carbonate, then you're going to make it where you can't make calcium carbonate, you can't make shells. That's one of the main ones. Other ways that are kind of interesting about how this carbon dioxide in the ocean causes problems is, one, if you reduce the amount of shellfish, then all those animals that eat the shellfish as part of their food chain are interfered with. They do not live as long. They don't have as healthy of a life because there's less food to eat. So just the fact that the shells, so you say, ooh, I don't care. I don't like shrimp. I don't like crabs. I don't like lobster. Why you wouldn't like them, I don't know. But you don't like those, that's okay. But things like dolphins do. Other fish like to eat those shellfish, and if the shellfish are not available, then the larger organisms up the food chain do not get the food they need, and they turn out being dramatically decreased in their population. So that's bad. Also, there's some studies saying that the fact that you have that acidic nature because of the hearing mechanisms in some mammal communication within the ear bones, they don't form as well, so you can't have as good of mammalian communication, and that would be being able to have dolphins and whales understand one another. Now, what's interesting here in the same thing is in the first video they talked about how the clownfish, when you have a clownfish that has the calcium carbonate not available, its ear bones are going to be affected, just like the dolphin from the previous one or any mammal underwater. What that does is it's going to affect the balance, and as it's called here, a neurosensory system of that clownfish, which means that clownfish will not be able to communicate with one another. They won't be able to sense dangerous predators, and they are going to have a lower survival rate because they don't have the ability to sense those predators. And that's pretty much of an extreme situation, attaching carbon dioxide in the air to these clownfish, but it is another impact. So having the carbon dioxide get into the water to make the carbonic acid and all the steps along the way is going to have a significant impact on aquatic life, especially aquatic life that requires calcium carbonate or the carbonate ions for the growth of shells and or bones. Now, again, trying to get a feeling on how impactful this looks at the revenue in the United States in fisheries. Notice that of the fisheries, okay, you've got calcifiers, things that have shells, oysters and mussels, clams, scallops, lobsters, shrimp, crabs. That's almost half of the shellfish, half of the fisheries are pulling in shellfish. So that's food that we would be eating. Okay, that's not available. That's less revenue for fishermen. That's less of that seafood for us to eat. In addition to that, these 24% down here, they're not necessarily, they're not directly impacted by the loss of the shellfish, but these are calcifiers predators, meaning they will eat these calcifiers. So if these reduce, then these reduce, which means now we're looking at almost 75% of the animals that are in the oceans that are part of fisheries that are used for feeding us are going to be impacted by the fact that our oceans are getting more acidic. Now, you can take it one step further. These top predators, they usually will be attacking the calcifiers, but again, everything's connected. So we start messing with the amount of carbon dioxide. It gets into the water, that makes the carbonic acid, it changes the pH. It spirals to essentially all aquatic life and has a major economical impact on the fishery industry. Other things to notice, there is a reduced fertilization in coral. So again, if you don't have the ability to create the components to fertilize coral, then the coral doesn't grow. So normally what you would have is this concentration of sperm that's from the coral would be reasonably high, a high percentage of fertilization because it's healthy, and this natural range of the ocean would be in this range. Well, when it's acidic conditions, you dramatically reduce the percent of fertilization. Less fertilization, less population growth, less coral seas. And when we get away from the calcifying organisms, we have an increase in the photosynthesis. What that means is now that photosynthesis is being increased. What's one of the products of photosynthesis? Well, it's going to use carbon dioxide to make sugar and oxygen. So a lower pH means more dissolved carbon dioxide. That's good, which means photosynthesis is going to increase. You're going to have a higher survival of the algae, but algae can cause all kinds of impacts, especially if it's an algae bloom and you're not getting the light into the deeper depths of the ocean where it's necessary. So algae having a higher population growth is not a great thing. And this is just a visual talk about the corals. So if you have what used to be here, this was early forms. You can see all the colorful corals. And as it tends to become more acidic, you see you have a higher concentration of the acid, but you notice the lack of coloring and lack of vibrancy to the coral, and then it just looks normal. As you have coral less being able to be reproduced and grow, and algae becomes more prominent, you have less biodiversity because you just have algae. And algae again causes issues with photosynthesis. So what can we do? Well, first off, how do humans impact this? Well, let's be honest. Factories. We like things like electricity. Most of our electrical plants, except for the ones that are nuclear powered, are coal burning power plants. Now, I'm not saying that a majority of the electricity is formed through coal, but a lot of it still is. More coal burn, more carbon dioxide, more ocean acidification, ... Pretty bad. Just us becoming more rural and more populated, we're making more and more carbon waste and increasing our carbon footprint. And the fact that cars have such a huge impact on carbon footprint, it's exponential. It's just insanely high that we have all these problems that are like good for us to feel like we're living a modern life. We're getting carbon dioxide into the air. We talk about reducing our carbon footprint, save the planet, reduce global warming, reduce climate change. But everything we try to do to say we want to have more modernized components, we tend to have a destructive nature on nature. So what can we do? So there's a couple things that are mentioned here that we can do. One of them is, well, if we don't have calcium carbonate, why don't we just add calcium carbonate to the oceans, right? If we add the calcium carbonate, you're going to reduce the amount of carbonate ion, which means the carbon dioxide is going to be dissolved, but you're going to add more of the calcium, add more of the carbonate, and you're going to have more calcium carbonate to make calcium carbonate. That's awesome. However, one of the challenges there, in theory, this works really, really well. In theory, this works really, really well. Where it's not working well is how much calcium carbonate you would have to use. So if I want to have my carbon footprint to be reduced by 2 gigatons of carbon in a year, just picking a number, 2 gigatons of carbon, I want to reduce the carbon footprint by 2 gigatons in 1 year. I would have to dump 20 gigatons of calcium carbonate in a year into the oceans. So I'd have to take 20 tons of calcium carbonate for every 1 ton of carbon that I would want to remove from the environment. That's kind of bad, because where do we get the calcium carbonate? Limestone, which is a common rock, actually around here, common rock. One of the reasons why we have the cement factory out in Union Bridge is the fact that it's on a huge limestone deposit. So that limestone would be reduced, eliminated, be dumped into the oceans, just so we could try to get this ocean acidification under control. So there's a huge amount of necessary material to make this happen. Another thing that's discussed, and again, we have a video that I can show you, I put into your Schoology classroom, is called iron fertilization. So iron fertilization it changes the process of the biological pump that we talked about in the earlier video. If I can get the carbon dioxide to be more naturally reduced through this iron fertilization, the iron starts to pull some of that carbon dioxide out of the water and makes it a little more aggressive. Again, what's the impact? I got to dump iron, fine milled iron, into the ocean so that it can react with the acid and try to make it where we have less acid in the oceans. It is a possible solution. Again, this video here, the second one, shows up on the next slide. I've connected this ocean iron fertilization video into your Schoology classroom, so you can watch it if you choose to. But it's a pretty cool process of just dumping iron ions into the ocean. So, and then the last thing, obviously, stop adding carbon dioxide to the atmosphere. Take those, be more inclined to use, like we have here, the nuclear power plants. I'm trying to read what's on that tower. Climate change, I don't know. Anyway, that's distracting. My ADD kicked in. Use more nuclear power. Use more electric vehicles. But there's a twist there. If that electricity is coming from a coal-burning plant, then you're increasing your carbon footprint by using an electric vehicle. So being very, very aware of using the appropriate vehicles, getting away from fossil fuels, will have a huge impact. Now, we're pretty modernized. Is this going to happen overnight? No. Is this something that we have to continue to aggressively pursue? Absolutely. The more carbon dioxide we get in the air through the burning of fossil fuels, the more we're going to be destroying not only our air, but we're destroying our oceans, which means we're destroying those living creatures that are in the oceans that may be a food source for those of us on land. So, ocean acidification, bad. It's just carbon dioxide being dissolved into water and causing the water to be more acidic. But we can do some things to combat that, even if it's small chunks. Everything you can do to reduce your carbon footprint is going to have an impact on reducing the amount of destruction to our oceans. So that's the end of this video. Hopefully you found it entertaining, or at least something that you think about. Ocean acidification is a bad thing, but it is definitely part of the process of getting carbon dioxide and reacting it in a pretty normal way. So I'm going to cut this off. You guys have a great rest of your day. Toodles.